Can you guys see my screen?
Yeah.
Okay, so the mole fraction is the number of moles of what we're looking at specifically over the total number of moles altogether. That's that specific solution, or the specific solute and the specific solvent altogether. So both of those together. So that would be your mole fraction. Now your mole fractions, your fraction of, again, this should be XA and this should be XB, should equal to 1. And that makes sense because it's a mole fraction. If you have part of one and the other part of the other and you add them together, that should equal to 1, right? So we're talking about solutions, right? And so we want to make sure that we keep in mind that we're talking about solutions. So it's important for us to make sure that we're distinguishing between which one is going to be our solvent and which one is going to be our solute, okay? And so that's going to also be very important for the molality, because the solute is always the one that is the least abundant. The solvent is the one that's considered the most abundant, okay? Let's see. Okay. So Raoult's law basically describes vapor pressure, and vapor pressure. So the vapor pressure of a solution is going to be the mole fraction of the solvent times the vapor pressure of the solvent. So if we sit there and we think about that mole fraction, and let's say we're working with water and methanol, where water is the more abundant, and we have 25, crazy. We have 2 moles of water, and we have 1 mole of methanol. So how would I calculate the mole fraction? You know, this is a participatory force, right?
1 mole over the molecular weight.
Okay. So would I use 1 mole of the molecular weight if I'm given moles already and I want to calculate the mole fraction?
Was that just your XA plus your XB?
So XA plus my XB is going to equal 1. So
Yeah.
this here represents my mole fraction. Right here, my XA. So again, mole fraction is the part over the whole, right?
Okay.
Okay, so the part over the whole. So the part, which one would be the part and what would be the whole in this case? So if I want the mole fraction of water, which is my solvent.
So then the part would be methanol? Because the whole is the H2O?
Would the part be my methanol? Because think
So
part
no.
and the whole, because remember the whole represents the solution all together. So I'm putting methanol and water together. So here's my thing. I have a glass of methanol. I'm gonna use MEOH. So I don't have to spell it all out. Okay. I put that in there, and then I put in water as well. So I have a cup. I put in my methanol. I put in 1 mole. One mole of methanol. Then I put in 2 moles of water. So if I'm looking for the mole fraction of water, what is going to be my part? What is going to be just the little part that I'm looking at, and what's going to be the total?
Would the solvent be your part and the total would be the solution?
That's right. So my solvent in this case is going to be my part. So my moles of solvent over total moles in solution. Okay, so in the case of we have 2 moles of water, what am I going to do?
So would it be 2/3?
That's right.
So it's just, can we justify saying that the part is just the part that we're looking for?
Exactly.
Okay.
That's exactly what I'm saying.
Okay.
I know it's early morning. You guys haven't had your coffee, and you're cranky because you haven't took your test, and so you're like, I really want to take this test. So
You got it.
okay, so what is that? 0.66. And so that would be the mole fraction of the solvent. Okay, does that make sense?
Yeah.
Yeah.
Okay, so if we assume that we had our solvent has a 0.79 partial pressure, the way that we would use Raoult's law, we say the solution, the vapor pressure associated with the solution would be that 7.9 times that 0.66. Okay. Oops.
So would that be just atmospheres because it's pressure, right?
Right.
Okay.
Exactly.
So 0.52.
Okay, pretty simple, right? It's not too hard. So you guys kind of understand what that part over the whole means?
Yeah.
Now, anytime that you make reference to any type of fraction, right, it's always going to be, particularly in chemistry, I should say, specifically in chemistry, it's always going to be the part, a specific, either element or a specific. So this is going to be kind of applied throughout everything. You guys did mass fractions back in the day, last semester. You just kind of think about more generally, because we're going to use a lot of terms that are going to be kind of recycled in a sense. So just kind of get in the habit of thinking about it along those lines. Okay.
Okay.
Questions, concerns, Catch?
Dr. Henry,
Yes.
where'd you get the 0.79 from?
That's going to be given to you. Usually the vapor pressure is given to you. So I was
Okay.
assuming that the vapor pressure was 0.79. Good question. Okay.
Yes.
Let's see. Okay, so vapor pressure of a solution containing 53.6 grams of glycerin dissolved in 133.7 grams of ethanol is 113 torr at 40 degrees Celsius. Calculate the vapor pressure of pure ethanol at 40 degrees Celsius. So how are we going to start here?
Well, you need your grams to moles, right? Because everything is in moles.
That's right. We need to change grams into moles. Okay. So for the glycerin, we have what, 53.6 grams. Okay. So how do I calculate? How do I convert to moles again?
Divide by the molecular weight.
Yes, yeah.
Okay. So what is the molecular weight?
3 plus 8.
12 times 3.
So 92.
Okay.
Mm, 5.8. 5.83.
Okay. So what do you guys get?
0.583 moles. Let's see.
Excuse me.
Rona. No, just kidding.
Well, I'm not too worried about it. I got vaccinated, so. Oh, and I want to take a minute to talk about that. There's two things I'm supposed to talk about today. Remind me at the end, save some time. Okay, so that gives us the number of moles of the glycerin. What about the ethanol? What do we do?
Need to convert that as well.
That's a 5. I'm having trouble with my pen today. There we go.
So that would be 46 grams per mole.
Okay.
Would it be 2.91?
2.91.
I second that, Abby.
Okay.
Good job. So limiting.
Oh. Okay.
So the ethanol is the solvent because it's most abundant.
Okay.
Okay. So then you take that over the total.
Okay, so we go my mole fraction of the solvent.
$291.
Oops. I don't need to do that. What do you guys get?
For the total or for everything?
For everything.
I got 0.833.
Me too.
Yes. Not alone.
Okay, and it's going to be unitless because you basically have moles over moles. Okay, so then what are we going to do next?
Your pressure.
Okay, so how do we do that? What is the equation that we're using?
Pressure times the solvent.
Pressure of what? Is that the pressure of the solution, or is it pressure of
Oh,
the pure
Total.
solvent?
Isn't it total?
Mm.
Solution.
Are
Oh,
you sure?
I don't know. I put solution down on the last note.
solvent, isn't it?
It's the solvent. Yeah.
Oh.
So it's the mole fraction of the solvent.
Oh, because that's what we used.
That's right. And
That makes sense.
pressure of the solvent. And then that's going to give me my P of solution. Okay.
Does it
So-
have to be in atmospheres?
Nope, it doesn't have to be in atmospheres because the units that you're using are, well, the mole fraction is unitless, right? And so whatever unit you're using for pressure, you can use get the same unit. So
Okay. So then you take 113 times
so what am I given? What is that 113?
4.
Is that solution or is that solvent? And what am I looking for?
Is dissolved in. Yeah, so that's the total, isn't it?
Yep. So that would be our solution. So that would be the vapor pressure of our solution. So we would have 113. Oops. All right. My head says one thing, my hands say something different. Equal 0.833 times P solvent. And we solve for P solvent.
So you just divide by 2.
Okay, questions, cash, credit?
So you need 3 sig figs, right? So 136 torr.
Oops, thank you. Even though I keep putting atmospheres. See, again, my brain is not functioning today. How many of you guys are graduating this year?
Yes.
Me,
By the way, tell Kayla congratulations. She got into San Luis Obispo.
Woo!
Congrats.
Congrats.
Get it, girl.
Thank you.
Okay. Pretty simple. It's not too hard. You just got to remember what is going to be your solvent and what is your solution, right? You should remember those definitions. You should know them like the back of your head, right?
Yep.
Good, good. Okay, so let's do something a little more challenging. Kind of like your lab.
Wait, we're not talking about that.
We're not talking about that.
Nope. Too soon, Dr. Henry. Too soon.
Okay, so these are some of the equations that are involved in colligative properties. Colligative properties, again, are just basically taken into the context that you have these type of interactions, those physical intermolecular interactions, right? And so that basically means that we need to sit there and take those items into consideration when we're looking at it. Okay, so let me give you guys a couple of the definitions and then we'll go through and do a problem. Okay, so the first one is so this is called the elevation, an increase in elevation point. So when we talk about a boiling point, you guys are all familiar with that. That means the temperature that where things are going to be boiling at. In this context, we have to use the molality or mola. Okay, so we know that molality is moles of can't even think straight, moles of solvent over kilograms of, moles of solute over kilograms of solution. Write that down. So I said it wrong. You know that M, that little m equals moles of solute over kilograms of solvent, not solution, solvent. Okay, now when we talk about this again, we know that the solute is going to be the least abundant component and the solvent is going to be the most abundant component. So when you guys were doing your experiment with the salts, what was your solute and what was your solvent? Yeah.
the water was the solvent
Okay.
and the salts were the solutes.
Okay. Okay. Pretty simple, right? Not too hard. Not much to think about. So in this case, KB is just a molar boiling point constant. So it's an elevation constant. It's going to be the same for that particular solvent, right? And so each solvent is going to have a different constant. Water has its own constant. It's KB, I can't remember off the top of my head the value of it, but it's going to always be the same for water. If we were talking about methanol, it's going to have a specific constant. It's always going to be the same for its constant. So there is I call it the chemistry Bible. And so there's basically tables and tables and tables and tables of different solvents that you can use. And it has all of their elevation constants and all of their freezing constants, or freezing point constants. Okay, so the same thing is this in the case of freezing point. So when we're trying to calculate the freezing point, we have to take into consideration the molality as well. And we also use that constant. Same equation, just your constants are going to be different for freezing than they are for boiling. Okay, questions?
No.
So let's see how we're going to use this. Oops. Oops. Okay, I think I went too far. Oh, there we go. Yeah. Okay, so here is an example. Calculate the molecular weight of a compound used in antifreeze for 0.243 grams of an unknown solute dissolved in 25.0 milliliters of water with a freezing point of 0.201 degrees Celsius. Actually, let me take one step back. So this delta T is going to represent the change in temperature. So you have your normal freezing point, and then you have your freezing point that's going to be associated with that change. And so it's going to be the difference of that. So your delta is going to be the difference of the two. Does that make sense? So like, for instance, if we're talking about water, what is the boiling point of water?
100 degrees
Celsius.
So 100 degrees Celsius. So that would be our reference. And then we subtract that, or we subtract what the boiling point is after we add our solute, because we'd assume it's going to be greater than 100 degrees, because that's typically what happens. Let's say it was 125, right? So then this guy would be that elevated temperature. Does that make sense? And so what we're actually calculating is just the difference between our boiling point and what it's gone up to. Does that, you guys get that?
Yeah.
Okay. Same thing with freezing point. Okay, so now we can go back to this. So calculate the molecular weight of a compound used in antifreeze for 0.243 grams of an unknown solute dissolved in 25.0 milliliters of water with a freezing point depression of 0.201 degrees Celsius. The Kf for water is 1.86 degrees moles, or molality. Okay, so what equation am I going to use to start us off? And what is it that we're looking for?
It would be the KF
Okay.
equation.
Okay, so we're going to use that delta T. Equals Kf molality. Okay. So what is it that we know? What's our givens?
The KF.
So we know our Kf. So Kf is going to be 1.86 degrees C. What else do we know?
Grams of solute.
We know grams of solute. Which is 0.243. What else do we know?
The freezing point depression,
So that's what in this equation?
is that the change of temperature?
That's right. So our delta T. Okay. And what is the last thing that we know?
25 milliliters of water.
And we have 25 mils of water. Okay, definition of that M again is what? M equals,
Molality, right?
it's molality, but what is the specific definition?
It was the moles of solute over kilograms of solvent.
Moles of solute over kilograms of solvent. So we know in this case, because they tell us, our solvent, because they say dissolved in water, that let us know that that's our solvent. And if you guys corrected me on that.
I just saw it when you went to go. I was like, wait, what?
So how can I change my 25.0 milliliters of water into kilograms? Oh, and also just for kicks and giggles, how do I calculate number of moles? Generally, moles equal, I should just say N. N equals what was
Molecular.
that? Molecular weight. Or molecular mass over or grams say mass. This is horrible. We're using M for everything. Let's see, we'll just write it out. Mass over molecular mass or molecular weight. Oops. That's the thing about science. We have to recycle so often.
Gotta be different. Get
No.
your people together.
The problem is that we run out of alphabets. We're using the Greek alphabet. We're using our alphabet. We should start using the Chinese alphabet or something like that.
So for your solution, wouldn't you need to convert to like cubic centimeters or whatever? Or isn't that, no, that's not how you do it. How did we do that last time?
What do we know about water?
Was it 1 gram?
1 gram per what?
Per 1 milliliter?
1 gram per milliliter. We know the density. The density of water is 1 gram per milliliter. And obviously it starts off as water, so let's go. So it's
Just 25.
Okay, so then we could use that. We know that it's going to be 1/1 over, but we have to convert that to kilograms, right? So how many kilograms are in a gram? Or how many grams are in a kilogram?
1,000 grams in 1 kilogram.
Okay. So that's 1, 2, 3. So that's 0.025 kilograms. Okay. So we have 0.025 kilograms. So if we go ahead and plug in everything into our equation here, right? And we want to solve, we're looking for the molecular weight, right? I'm going to start using MW for molecular weight. Okay, so if I want to solve for my molecular weight, I need to plug all of this stuff in. So I'll get my, delta T divided by Kf equals molality, which is going to be equal to mass over molecular weight and that's all going to be under my kg of solvent. Well, we know our kg of solvent, so we can move that over to the other side. So we'll have delta E kilograms of solvent divided by Kf and that's going to equal mass over MW. And we're going to get MW by itself. Yes, if I move that density of water. So we'll get MW equals mass Kf over delta T kg solvent so then it's just plug and chug, right? So we just have to plug in our grams of salt of our solute. Times our Kf, which is 1.86 degrees C molal over our delta T. Over 0.025 kg. And so our MW will be, what you guys calculate,
$89.95.
yeah, 89.95.
I'm trying
Yeah,
again. Hold on. Yeah. I don't know.
Okay, 89.95. Stick fix.
B3.
And that's grams per mole. Okay. Questions, concerns, Cash, Ola? Okay, so you guys will kind of notice that like from here on out, a lot of the stuff is just you have these nice little beautiful equations to work with and you're plugging stuff in, right? So you're using all the stuff that you knew before and you're applying it. Is that making sense?
For the
Yeah.
most part, yeah.
Helena?
Yeah, it's a lot. Like everything, it's like everything we know all jumbled in one problem.
And one problem. Exactly. See, but I've been training you for that. Think about all of my short answer problems. I've been building you guys up for this.
I'm crying low key.
You're always crying, and then you always do well on the test. I want to hear it from you.
Doctor, and you have a question.
Yes.
So how did the kilograms cancel out on this problem? That's what I'm trying to figure out.
Because this unit here, the KF, is 1.86 degrees Celsius over molal, and we know that molal is moles over kg.
Oh,
So
okay,
we-
okay.
Yeah,
I
so
see it now.
that's how it is.
Thank you.
No problem. Yeah, its own specialty type of units, right? Okay, so you ready to move forward? Okay, good. That means that you guys are ready to move forward even faster.
I guess. I mean, we don't have other option.
That's true. There's no options. Okay, so when we talk about osmotic pressure, it's the osmotic pressure typically deals when we're talking about membranes. And then so a membrane that only allows a solvent through, but not a solute through, is called a semi-permeable membrane. Okay, and because we have these semi-permeable membranes, we're going to be putting pressure on it because those solutes are not able to sit there and flow readily through that process. Okay. So, so if that membrane is permeable, and we have solute on one side of that membrane, and we have the solvent flowing, right? And so basically what happens is the solvent will flow through the membrane to sit there and try to balance out the concentration of the solute on the other side. And so that movement is called osmosis, okay? So when we talk about osmotic pressure, we're talking about the pressure associated with that movement, okay? of our solvent to try to equilibrate both sides of the membrane. Okay, so in the case of our cells, so we're talking about biology, the cell membrane is a semi-permeable membrane. It will let certain things pass through and other things it won't let pass through. And because of that, it goes through that process of osmosis. And so in that case, we're looking at the inside of the cell versus the outside of the cell. Does that make sense?
Is this just diffusion?
Yeah, it's just diffusion. Osmosis is just a special case of diffusion.
Okay.
Okay. So if we have our cell, and then if the solution, if the solute's concentration outside of the cell is greater than inside of the cell, right? That is considered to be hypertonic. If the, and then I'll tell you how things work in that case, right? So if it's even to the inside and the outside, it's called isotonic. Yep. And then if the concentration on the inside is greater than the outside, that's called hypotonic. And so we make reference, when we make this reference to it, we're making reference to that outer side. Outside is like the reference point, right? So that outside, if it's greater, hyper, meaning more. If the stuff on the outside is less than, hypo, right? Does that make sense?
Yes.
Yep.
Okay.
Now you're speaking my language. Finally.
Now, now I promise you, I will have a question on this, not on this test, but on our next test. You'll have a question like this. It'll be multiple gas and talking about hyper and hypo, or multiple gas or matching, something like that. Okay. If I can get the images. Okay. So let me go back one more thing. So in the context of hypertonic, in a hypertonic situation, what's going to happen to the cell? If it
It's going to draw it in.
Is it going to draw it in? What do you mean by draw it in?
Well,
So now remember, the cell is going to be about 75% water, right? So what's going to happen to the water, because that's our solvent, is it going to be going inside the cell or is it going to be going outside of the cell?
Inside.
Are you sure? So the concentration is higher on the outside of the cell. That's hypertonic. In the case of hypertonic, if the concentration is higher on the outside of the cell, which way is the water going to flow?
Outside, right?
It's going to be flowing outside. Yeah, because it wants to balance it out. It wants to get to equilibrium. And this is the key point about everything. This is, we're building you guys up to understand equilibrium. So it wants to get it so that the concentration on the inside and the outside are the same. So it's going to move that water on the outside. Okay, so then that causes the cell to shrink up. Okay, you get that? Oh shit, that's pretty bad. Okay, so what I need you guys to do, how many of you guys have eggs?
Yes.
How many of you guys still have vinegar?
I don't have vinegar.
You don't have vinegar from your kit?
Oh, yeah.
There's probably tons of vinegar in there, right? So what I'd like you guys to do is get 3 eggs, put them in vinegar, and a little cup in vinegar. You can put them all in the same cup, get them all to fit in it, or a little bowl or whatever, in vinegar. So, and let it sit for about 2 days, 3 days. Okay.
Do we crack them open or just with the full egg?
You want the full egg.
What
Don't
is it
crack
gonna
them,
do?
okay? And then we'll be doing an experiment on, hopefully on Wednesday. So it should take you 2 days to do it. Sometimes it take a little bit longer, but if not this Wednesday, it'll be next Monday.
So not this Wednesday, next Wednesday?
No, if not this Wednesday, next Monday.
Oh,
It
okay.
should take you 2 days, but it really just depends on how well it sits. This is just prep for your experiment. So,
3 eggs.
and also the concentration of the vinegar. And I can't remember offhand what percentage we gave you. And I'm also finding that they said 1% of one thing, but they didn't necessarily give us that. Okay. The equation for osmotic pressure is pi. This is a capital pi, which looks very much like lowercase pi, equals, in this case, molarity, capital M, R, which is the ideal gas constant, times T, which is temperature. Okay. Are you with me? You got it up here? So if you think about it, N over V equals molarity. So you're basically just using pi as a kind of very general term using the ideal gas law. So you're basically using the ideal gas law. PV equals nRT. Piece cake?
Yeah.
Good, good. I know you guys are excited now. We get to the gritty. Okay, let's use this equation. Okay, osmotic pressure calculations. Let's see, a 10.0 gram sample of liver enzyme catalase has a volume of 1.00 liters at 25 degrees Celsius. The osmotic pressure at 27 degrees Celsius. The osmotic pressure at 27 degrees Celsius is 0.744. Calculate the molecular mass of the catalase enzyme. Okay, so how would I go about doing that? So what are we given? Lena, what are we given?
10 grams of
10 grams.
liver enzyme.
Okay, so we have 10 grams of our enzyme. Okay, what else are we given? Abby?
Mm,
We have mass.
so then we. Are we getting the. What's it called? Oh, God. Are we gonna go and get the volume?
Are we gonna go get the volume or is it given to us?
It's given to us.
Oh, it's given to us. So we have the volume. Oops. Okay, what else are we given?
The osmotic pressure.
We're given osmotic pressure.
What did you say, Dr. Henry?
Anything else are we given?
Temperature?
I heard somebody saying underneath the graph. Temperature. And
Which
which
is
we know we
what?
have to convert to what? What units we have to convert to here?
I hear you, Dr. Henry.
Okay, I can't hear anyone now.
I know, I thought it was just me. I thought I was just going hard of hearing.
Okay, now I can hear someone.
So we want to change it to Kelvin, right? Are you
Yeah.
guys there?
Yeah.
Okay, so then that is okay. And what else are we? Oops. What else are we doing? Is that it? What is it that we want to calculate?
We want to calculate the molecular mass.
The molar mass. Okay. Okay, so we want the molar mass. I'm going to use MW for this again instead of all of our MMs, because otherwise it's going to go real quick. Okay. So we know that the equation that we have is pi equals molarity times RT. Okay. So we're given pi. We know molarity. What is the definition of molarity?
Moles over liters per liter.
Okay, moles. So we'll use N for moles over volume. Okay, and we know moles, N equals mass over molecular weight. Okay, so we can plug all of these into our equations. So we'll get equals mass over volume and molecular weight. Now, if I make a mistake, you guys are responsible for correcting me. Okay, so then we want to solve for, oops. You guys are just going to let me keep making that mistake. We're going to solve for MW. Which is going to be mass RT over V pi. Our mass was 10 grams. RT, what is R? 0.0821. And I have super ears.
Can you not hear me?
Okay, but we know that R is ATM liters. So our pi, we have to change, our pi we have to change towards ATM. How do I do that? One ATM equals how many torrs? Anybody remember?
Nope, it's like 700 something, isn't it?
760? That's pretty good. You at least got it in the ballpark.
Yeah.
I think you guys have a table. Did I give you guys a table with all the pressures?
Yeah.
I think so, yeah.
Abby, can you hear me? Can you guys hear me?
Yeah.
Yeah. Abby can't. Did you hit your volume, Abby? Hey, I can hardly hear you, Cassie. And I keep going soft. Man, don't you hate technology? It's driving me
It's
crazy.
wonderful.
And lately everything is going bad. I mean, okay, so if we did the math, let's go. 9, 7, 4 times 10 to the -4 ATM. Okay, so we put our volume. Oh, gotta put our temperature, which calculates to 300.15 Kelvin. Our volume, which was 1 liter, and our ATM, which is 9.74 times 10 to the -4. Are you guys at least seeing it? Is your screen? Yeah, so it's still working that way. So
Okay, I can hear you again.
you can hear me again?
Yes.
Aha, my
Like
solution worked.
it goes away and then it comes back.
I know that's what Cassie was saying. Okay, what did you guys get? You got 0.24? This is what I got. Yeah, so molar masses for enzymes are pretty heavy. So
Where am I getting it wrong? Because I'm still getting.
so you're not forgetting 9.74 times 10 to the -4,
Nope. 10
because that's going to make your value much bigger. And this Wednesday, the last thing that I need for for making wine or kombucha is coming in. So this Saturday I will be on campus in Coalinga. So those who are in that area, you can pick it up there. I know that Taylor is in Lemoore, so I can probably drop it up. Pretty much I can drop it off to all you guys along the way. So, because I know Taylor's in Lemoore, I know that Mauricio is in Huron, and I know that Selena is in Avenel. Although your sister's going to be on campus but she doesn't know it yet. But your sister's going to be on campus on Saturday, so you can get it from her then. And then I know Kayla is in Coalinga.
Yep.
And Abby, are you in Lemoore?
No, I'm in Huron, so I
You're in
can either
Huron.
go to Lemoore or Kalinga.
So actually I can just drop it off at Huron as well too, because it's along the way, depending on which way I decide to go. So I'll just drop it off. Okay, so then I will hit you and Mauricio up, you know, when I'm driving into campus on Saturday, which will probably be around, what time we met? 11. I mean, we met at 1 o'clock. So we were supposed to meet at 11. So we'll probably meet at around 1-ish again. So.
Okay.
So I'll let you know on Saturday. I'll drop it off. And if you can't pick it up, just send somebody else to pick it up. I'll be at right next to the school, I think the elementary school. Can't remember which street it's on.
Elementary school in Kalinga?
In Huron.
Oh, Huron. Oh, okay. Yeah. I'll go there.
Yeah.
So this is for picking up.
So your stuff for making kombucha or wine. If you want to make wine, you have to have a valid ID.
Oh God.
You know, so I don't want no fakes at all. You know. And Sadie, you're in Kalinga as well, right?
Yeah.
Yeah. Okay. So I'll give it to you then. So you'll get all your little components at that point. So
So are you gonna send us out an email for the times we can?
I'll let you know the
Okay.
exact times. Yeah.
Cool.
Yeah, but because technically it got back ordered, and so it was supposed to be here last week, but it didn't come in, and so they pushed it back to this week. So it should be in on Wednesday. So if something else comes up, if you don't get an email from me, we're not meeting. Okay, but if you get an email, I'll send you an email either way. So to let you know what's on. Okay, questions, concerns, Cash?
Did you know they make hard kombucha now?
I know. I saw it actually in the store.
Yeah.
Wait, really?
Yeah.
Oh my God.
Yeah.
Yeah, what they do, they change the balance of yeast, and because kombucha actually makes a very low percentage, very, very low percentage of alcohol, because they use a yeast that's kind of defective in alcohol synthesis. So it makes low amounts.
I still don't know
Okay.
if I could jump on the bandwagon though.
Okay, so now when we start talking about colligative properties, when we start talking about those electrolytes, because electrolytes have more stronger charges than in the case of our covalent bonds, and so our covalent intermolecular forces. Okay, so before that was in the context of covalent intermolecular forces. Now we're going to be talking about ionic. And so when we have that dissociation of those ions, so those electrolytes in solution, then they're going to behave differently. Okay. So when you do that, we have to make sure that we account for the Hoff factor. Hoff factor basically is recognizes that you have this ionic compound that's been dissociated. And so you have those charges. And those charges are going to make things a little more stronger. So that's going to have a stronger effect on your temperatures in the case of your boiling point elevation, compared to like if we're just using sugar, right? Because adding sugar also will affect our boiling point, just because you have those dispersionary forces. But now we have to take in consideration the ionic components. Okay, and so what we do, we make a correction factor. It's called the Van Hoff factor that's added onto that. And that factor is just going to be the number of dissociated particles, right? So for instance, that you would have, okay? So if you have the calcium chloride, how many dissociated factors would you have? Oops. Brain is not working today. I have calcium chloride, Cl2. How many dissociation factors would I have? So if this guy dissociated, how many how many different particles do I have in solution?
3.
3. So then my I would equal 3. Okay, you guys get that?
Yeah.
Okay. Okay, so now this is going to be for all colligative properties. So that's going to be your temperature elevation. It's going to be for your in the case of your osmotic pressure. It's also going to be for your partial pressures, right? Or your vapor pressures. Okay, even though it's not written down here. Okay. Okay, so so calculate the freezing point for a solution of 0.74, say 0.724 grams of calcium chloride solution in 175 grams of water with the KF of 1.86 degrees molal. Okay, so what am I going to do?
Would you use the IKFM
Yeah.
equation?
I KFM equals delta T. Okay. So we're talking about water, right?
Yes.
Okay. So we know that when we talk about our delta T, that's going to be water freezes at what temperature?
0.
Water freezes at 0. So if I go, it would be 0 minus oops. Zero minus T, so. Okay, we're talking about calcium. How many, what's gonna be I? I is gonna equal what?
3.
So I is gonna be 3. Okay, we know we have our mass of water. We need to change that to what units?
Moles.
We need to change it to moles?
Or
Kilograms.
Kilograms, right? So I have to go grams, 1 kg. And that equals okay. And we know that we have 0.724 grams of calcium chloride. And that's our solute. So what do I need to do to that? What do I need to do to that? We're gonna talk today.
Convert it to moles.
Convert it to moles. So calcium, I remember, is 40. Chloride is 35.45. So, and there's times 2. So that's what, 70.9. plus 40. What do you guys get?
0.00653.
0.00653 moles. Okay, so then so we're going to 3 times our KF, which is 1.86.
Where's the negative coming from?
Because we subtract 0
Oh,
minus that temperature.
Okay.
Good question, though. Then we have our molality, which is 0.00653 moles over kilograms, which is 0.175. Negative 0.208
Yep.
degrees C. Okay, and remember that's a times. Maybe I should make a little X dot there. It looks like a minus sign. Okay. Questions, concerns, cash, credit, Kool-Aid.
How did you get the negative again? I didn't hear.
Because the delta change in temperature would be
Right.
your T that you're starting at, your minus the T that you're ending at for your freezing point. So it would be the difference between those two.
Oh, okay.
So you get 0 minus T.
Gotcha.
Okay. Okay, so questions, no questions? Okay, so the last slide of this chapter is it's a novel, okay? So we're talking about colloids. So at this point, we kind of talked about our solutions. We have 3 types of solutions, or what we have. When we have solutes, we could have 3 types of things. We could have a solution, we could have colloids, or we could have a suspension. So solutions basically are suspended in solution in the solution, right? And you guys will see that, like when we add salt and water, it's suspended. Okay. Now, the difference between the 3 is going to be based upon particle size. Okay, so the bigger the particle, so if it's a big particle, then it's called a colloid, right? So if we put, have you guys seen those little beads that they suck up water?
Oh yeah.
Now usually, I didn't put any in your kit. I should have put some in your kit.
They're like water pearls or something like that.
Exactly. Yep.
Okay.
Okay. So those are an
Orbeez?
example. What was that? Yes. Say it again.
Orbeez?
Orbeez. Yes.
Oh,
Orbeez.
okay.
Yes. Yeah, the Orbeez. So those are an example of colloids, right? So if you put those in water, they're in solution, right? And they take up so much room that they're dispersed in solution, right? But they're so large. Okay. So now they're not dissolved completely in that solution, because you can see them still. So they're not readily dispersed through it, so that it's a very distinct solution, you know, kind of like, again, salt and water. Salt is kind of dissolved through that entire process, where the Orbeez aren't. Okay, so, or like when you have you guys made gravy before?
Yeah.
Yep.
And have you screwed up and didn't make your flour well enough, and you got those little clumps,
Yep.
flour clumps? So that's an example of colloids. Okay. Okay. Immersions are usually examples of colloids, because immersions are just basically you're whipping stuff up, and then basically you have like little balls of stuff that are all mixed together. Milk is an example of a colloid solution when it's not, when they haven't removed any of the fat and stuff from it. And so it's kind of, you can see the different layers and stuff that exist in it, the particles. Okay. Let's see, like soaps are an example, because they also are kind of colloidal, the way that they behave, because they don't really suspend in solution. So like if you put detergent in water, you can actually see the detergent go in there, but eventually those will somewhat suspend. But if you actually look at a closer level, they're not completely suspended like the others. Okay. Okay. Questions? Okay. Okay. Last thing is suspensions. So basically suspensions, again, they're going to be heterologous mixtures, and they're going to be larger than a colloid. So in this case, I guess the Orbeez would have been more of a suspension rather than a colloid, because they're so big. Okay, and the only thing is that suspensions will actually precipitate out. For instance, dirt. Right. So if you get dirt and you kind of mix it in there, shake it up, it's all in suspension initially, but eventually it starts precipitating out. So it'll drop down to the bottom. The dirt starts to settle. Okay, so if we go in terms of size, solutions, it's tiny. It goes into solutions, dissolved in solutions. Colloids are dispersed, and then kind of like flour, and then the last ones are like dirt. And you know, like flour kind of floats still, doesn't it? The little balls of flours, they don't sink to the bottom, they kind of sit up top still.
Yeah.
Okay. Okay, that's it. Questions, concerns, Cash? So I'm going to be posting, there's an opportunity to earn a couple of extra credit points. There is events that are happening this entire week that deals with Black student success. I will be posting it. It'll be every day this week at noon, including today. I'll be posting a link where you can register. soon as I can, hopefully before noon today. And I actually think that it was actually sent out to the whole campus as well. So if you look at some of your emails or messages that you guys received. So you can earn a couple of extra points. We'll say 3 extra credit points towards things.
So you said you were gonna tell us something earlier?
Yeah, that was the one thing.
Okay.
Yeah, and then I talked to you guys about the egg,
Yep.
and I'll officially put that lab up. And then something else too.
Wait, what lab are you putting up today?
I'll be putting up the egg lab, so the one that you're going to be doing next week, probably,
Okay.
more likely. And then the pickup for your kombucha.
Got it.
Okay, kombucha or wine. Okay, I will see you guys later. Have a good day, and then I'll give you updates as soon as I get the exam and stuff up. You guys, I'm going to give you enough time to get it done, so don't worry about it. I'll talk to you guys later.